Okay, so we have a combustion reaction in which we are putting a substance called biphenyl into a bomb calorimeter. They tell me that, and they want to know the delta E of the reaction. Now let's look at this bomb calorimeter. We're going to put the biphenyl down here. The C12H10 goes in this cup. That's a 10. And we put oxygen into the chamber as well. We set that down into the water, and that's called the bomb, and we ignite it, and as all combustion reactions will occur, it'll give off heat to the surroundings. So the water will heat up, but water's not the only thing that will heat up. The bomb will heat up, the container that holds this will heat up, this wire will heat up, everything will heat up in there, and we know how much it's being heated up by because they're giving me what temperature it started with and what temperature it finished with. In this problem, they're asking us to calculate the delta E of the reaction. Now, in the other problem we did in class today, we reminded ourselves that the delta H for a reaction is equal to the Q if it goes by a constant pressure environment. This is not a constant pressure environment. This is sealed off, and the contents will change. The gases that were in there and the pressure will change. This is a constant volume calorimeter. So we can't determine the delta H by knowing the Q. But this is what we know about delta E. Delta E equals Q plus W. And we know that work is minus P delta V. Since the volume is constant, then delta V is 0 and there's no work term. And that means that when we figure out the Q of the reaction, we will know the delta E. Now, it is true that delta E and delta H are nearly the same. So let's put nearly the same. Equal to each other in most cases. Okay, so they're very, very close to each other. And so a lot of times when we calculate a delta E, we just say, that is the delta H. But the fact of the matter is we are actually determining the delta E of this reaction. Now, how do we do that? By calculating Q. The Q of the system is equal to minus the Q of the surroundings. What is the system? The system is our reaction, Rxn. The surroundings is everything around it. And so if I knew the mass of the surroundings, the specific heat capacity of the surroundings, and the change in temperature of the surroundings, I could get the heat of the reaction. Well, they don't give me the mass of the surroundings. They don't give me the specific heat capacity of the surroundings. They give me something that's just called heat capacity. Well, heat capacity is the mass times the specific heat. So they are giving me these two things combined when they're giving me the heat capacity. So I will plug that value in of 5.86 kilojoules per degree Celsius. Notice in the denominator it doesn't have the mass that you're used to seeing when you have a specific heat capacity. This thing is going from a 25.8 up to a 29.4 degrees Celsius. You put in the you put the final temperature in first. It happens to be the high temperature here. It finishes here. It started at 25.8 degrees Celsius. So it's heating up, and when I multiply these values out, I get a number of a negative 21, because of that minus sign right there, kilojoules. Now this is the heat of the reaction, but it's only for us burning this much biphenyl. They want it for a whole mole of biphenyl. So we have to keep in mind at this point that this is how much heat is generated per this many grams. So it's a ratio that I know to be true. This much energy is given off when this much reacts. But I will put the grams in the numerator and the moles in the denominator so that I can finish knowing it in kilojoules per mole. The molar mass of biphenyl with its 12 carbons and 10 hydrogens is 154.22 grams per mole. And when I multiply that out, I get the value of a negative 6.3 times 10 to the third kilojoules per mole of biphenyl. Now this is the Q of the reaction. I look back up here and it says find the delta E of the reaction. Remember, in a constant volume situation, the work term is 0, and when we determine the Q, we have determined the delta E. So this is the delta E of the reaction.